There's a couple of outliers, right? We've been talking about the main reservoirs and the main sinks and sources, right? Photosynthesis, respiration, and the volumes in different places. One of the things that we didn't really talk about was permafrost, right? So in the kind of extreme north and extreme south, there are places where plants will grow for a part of the year. They essentially die, and they become part of the soil, but that soil is frozen, all year round. And so that carbon is kind of locked up in that sense. But we definitely have seen melting permafrost, although when we look at the source from permafrost, it's currently not an incredibly significant source of atmospheric carbon, that kind of decomposition reaction that should be going on, although it's frozen. If it melts, it decomposes, releases CO2 into the atmosphere. But with continued melting, it may well become a larger source in the future. So the next thing that we're going to get into is we're going to get wet, right? We're going to talk about the ocean-atmosphere interface. So the chemistry that's important in this case is to note that CO2 as a molecule is readily dissolved in liquid water. It's not true in solid water, but in liquid water, CO2 reacts with it pretty easily. You've experienced that when you open a soda or a beer or your champagne or heck, anything that's carbonated. That's dissolved CO2 in that fluid, and you can kind of modify the temperatures and the pressures, and you can get more CO2 to dissolve in, like really super carbonated things or something. So that's one of the primary sources for getting CO2 in the ocean is actually rainwater and also surface interaction. So whether that CO2 is stripped out of the atmosphere by falling rain as it interacts, or at the surface of the ocean, what happens is CO2 will combine with H2O. I know at this point you're probably just rolling your eyes thinking, like, I did not think I was taking a chemistry class. Chemistry is important, right? Especially if we're going to understand climate change. And it produces this compound, H2CO3, which is carbonic acid. It actually produces a very weak acid, which means rainwater, as it naturally falls, is naturally acidic. It has a pH of, I think, about 5.8. I might be wrong. You could double check. Maybe I'll edit it and put it down here on the bottom. So this process we generally call ocean acidification. Well, it sounds scary, and it kind of is scary, right? The ocean is important to us, right? We get a lot of food from the ocean, and it's a big part of our planetary system, right? Interactions with the atmosphere, the kind of geosphere, the hydrosphere, of course, and the biosphere, right? Things live in the ocean. So when this happens kind of related to the amount of CO2 in the atmosphere, right? So if there's higher amounts of CO2 in the atmosphere, ultimately they flux into the ocean and make higher amounts of CO2 in the ocean, which makes the ocean more acidic. If CO2 is stripped out of the atmosphere, we get an increased kind of diffusion reaction going the other direction, and then the ocean's not quite as acidic, right? So it scales with the amount of CO2 in the atmosphere. So we're talking volumes here, about 80 gigatons carbon on an annual basis going down into the ocean. But actually that diffusion reaction that I was mentioning returns also about 80, right? So again, we like to see things in steady state. One thing we haven't really kind of gotten into yet is what we did in the last description, which was volumes of carbon. And for that discussion, we really have to think about the ocean in two parts, right? So there's the shallow ocean, like the upper 100 meters, that's about 300 feet. That's the kind of well-mixed portion of the ocean, the mixed layer, if you will. And then down below that, we get what we call the deep ocean. And that it doesn't interact with the atmosphere, but it does interact with the base of the mixed layer. So thinking about how this interaction is going on with the atmosphere, the ocean, rainwater falling in. Again, we've got this mixed layer up here near the surface. There's wind blowing across the ocean. It churns along pretty good. That's also where most things live, right? Things like to live where there's sun, right? We've got the photic zone, and so the upper portion of the ocean has a much higher biological content as well. So in terms of overall carbon, there's about 900 gigatons of carbon in the mixed layer of the ocean, which is not that far off of the amount of carbon in the entire atmosphere. And remember, there's this diffusion reaction, right? Kind of balancing between the mixed layer and the atmosphere. It's coming in, it's going out. Hopefully in steady state, right? At least where we start our models, we talk about things being in steady state, and then we can talk about how they kind of diverge from that. But interacting, at least with the base of the mixed layer, is what we call the deep ocean. And that's a pretty big deal. So if we think about the volumes of carbon in the deep ocean, it's big time, right? About 40,000 gigatons of carbon are sitting in the deep ocean, and that has a very long residence time. So it does interact essentially by ocean currents, right? We've got downwelling currents and upwelling currents, and that's how carbon can cross this threshold. Once it's in the mixed layer or the shallow ocean, then it can kind of interact with the atmosphere. But this process is very slow. When we start looking at it in the big picture, it's actually not the slowest part of the carbon cycle. It does hold far more carbon than the atmosphere. Remember, the atmosphere had about 850 gigatons of carbon, mixed layer about 900, but 40,000 in the deep ocean, which is a lot. And not only does it interact with the base here of the mixed layer and get carbon in that sense, but also when things die, that ultimately becomes part of the deep ocean, right? If you've got a whale swimming along and the whale dies, well, it'll probably float around for a while, but eventually it becomes what we call a whale fall, which is fun. You can look up whale fall on YouTube. That's always a good time. And also, everybody poops, right? So things in the ocean, as they're consuming other carbon, they defecate, and that drops down and settles in the bottom of the ocean. Some of it ends up in sediments, some of that diffuses into the seawater. So that's the source of deep sea carbon.